Next, we have Dr. Bridget Scanlon, a senior research scientist with the Bureau of Economic Geology from the University of Texas at Austin, where she leads the Center for Sustainable Water Resources. This morning, she'll be outlining the physical connections between climate, groundwater, and surface water.
Thanks. I'd like to reiterate what Philip said. Maybe not sure you needed to import a Texan for this either. But anyway, I appreciate the opportunity to talk today. And so I'm going to look at groundwater surface water connections, and I would like to acknowledge Claudia Font from the USGS. And I'd like to put in a plug for the USGS, actually. You know, there's a lot of emphasis these days on remote sensing and NASA and modeling and all that sort of thing, but there's nothing, I think, to replace boots on the ground and data collection, which I think is on the decline, and we think we can replace some of that with remote sensing and other things, but it's hugely important and going to be even more important in the future. And then I'd like to acknowledge some of the other colleagues, Laurent Longburn and Dee Long, who were both postdocs with our group, and Bob Reedy, who is a colleague. So just briefly talk, to give some background and then talk about the Central Valley, going from pre-development, groundwater depletion, conjunctive use of surface water and groundwater, and drought impacts, and then compare it to the high plains. And this was a study that Claudia and I did a couple of years ago, and I really found it very insightful to compare the two regions, and then approaches towards more sustainable management and focusing on managed aquifer recharge, which I think is the best thing since sliced bread. So looking at the global picture, this is the output from Petrodol's models. You can see that water withdrawal at a global scale is dominated by irrigation. 73% of withdrawal, 86% of consumption. And so I think it's very important to keep that in mind when we're talking about water issues, how much food production and irrigation controls our water use. And so when I'm at presentations, a lot of presentations in Texas are related to the oil industry, and some people talk about what's the elephant in the room, you know, and to me it's irrigation and all the water use associated with it. Energy, I mean, hydraulic fracturing may be problematic for water quality, but it's less than 1% of the water use in Texas. And it's important to keep these numbers in perspective. So this is output from another modeling analysis that Petrodol and her group did. And basically what it's showing is that we see a lot of papers these days on groundwater depletion, but here is actually showing where there's increase in groundwater storage in different regions. And the blue areas are where there's increase in water storage, and the brown, dark reddish colors are where there's reductions. And so the increases in storage are caused by irrigation with surface water. And examples include the Nile, Tigris Euphrates, although there's been a recent study from Grace suggesting that there's a lot of groundwater depletion there. Indus, southeast China, where you're irrigating with surface water. And we've seen this in California when you had all the transport of water from the north to the south, as Ruth mentioned earlier. You then had a lot of irrigation with surface water and then replenishing depleted aquifers and recoveries of up to 100 meters. So that sort of conjunctive use. So you could call that conjunctive use sort of a managed aquifer recharge, except we don't use that term for it. But when you irrigate with surface water in areas that you're irrigating with both, you can replenish the groundwater when you're irrigating with surface water. Most places, when they irrigate, though, they either irrigate with surface water or groundwater, and few places can switch back and forth like they do in California. So Lenny Konikow did a nice analysis looking at depletion in different regions in the US, and here you can see the High Plains aquifer is top of the list, and the Central Valley with depletion from 1900 to 2008. And it gives you an idea of different systems that have been depleted that are being depleted over time. So talk briefly then about the Central Valley region. And of course, as Ruth mentioned earlier, you have a lot of surface water coming in from adjacent mountains. And so even though it's the valley itself is a fairly small area, the watershed itself contributing to the valley is quite large. And USGS estimated about 1,000 cubic kilometers, 1.23 million acre feet per cubic kilometer. So that's, you can consider these similar in million acre feet if they're the units that you're used to. And we've depleted about 14% of that. But you have a lot of issues here. If you deplete, you can't consider that you could take all that water because you've got subsidence issues, seawater intrusion and stuff. So how much water do you have that you can use is a question mark. So before they started irrigation in the Central Valley, this is a pre-development water budget that Claudia has in her regional groundwater model. And you can see that the input to the system from recharge from precipitation and streams, about 2.5 cubic kilometers, matches the output from evapotranspiration and stream discharge. So basically the water flowing in from the boundaries of the valley then discharged to the streams and are discharged as riparian ET. Then when you started development and irrigation, you changed the system quite a bit. And so this is the budget that you have then after you started irrigating. And this model is from 62 to 2003. So you increased recharge a lot. I mean, previously we saw 2.5 cubic kilometers input into the system per year. Now we've got recharge from precipitation 14 cubic kilometers and from the streams. And then, of course, you've got this large pumpage to support irrigation. And then ET and stream flow. But the net is a negative. The long-term average is a negative of about 2 cubic kilometers per year. So even in normal, and that's much more during drought years. So you basically speeded up the hydrologic cycle quite a bit. And then, of course, so this is the map from the 60s then showing the huge depletion, particularly in the southwestern part of the San Joaquin Valley, and the related subsidence in that region. And this was a really nice article in National Geographic where they talk about the California's pipe dream, where you've got all this piped water then with the state and the federal projects bringing water from the wet regions in the north to the dry regions in the south, reversing that groundwater depletion then and replenishing some of those aquifers. And then looking at the situation from 1960 to 2003, and this is the output from the regional model, you can see the impact of the 76-77 drought when you had large depletion of groundwater storage. And then the 87 to 92 drought, again, a huge depletion of groundwater storage, and then later. So heavy reliance on groundwater then, and then not enough. I mean, you did have a recovery after 76, 77, so that was just a one-year drought, but then not enough to replenish what you took out during the drought after this time. And then this is the depletion. That's the black line was the entire Central Valley, and this is the depletion in the Tulare Basin in the south. And then basically up and down in the northern basins, the Sacramento Delta East side, but no net long-term depletion in those. So it's all concentrated in the south. So I've been in meetings where people think that we've discovered groundwater depletion since we've seen GRACE, and that's kind of tough on groups like the USGS who've been studying it since the 1900s. But it has brought the public attention to groundwater depletion, which is nice. And many of you may be familiar with the GRACE, the satellite, twin satellite to monitor gravity changes that are related to water storage. It's important to remember that the GRACE satellites measure total water storage. And so in order to estimate groundwater storage, then you need to subtract all the other components. You need to subtract the reservoirs we usually monitor, but the soil moisture component is difficult to estimate because we're not really monitoring that very well. And there's a lot of variability among the models. So then looking at the Central Valley with the more recent data, then looking at GRACE and the other storage terms. So this is total water storage during the recent drought, 2007 to 2009, 40 cubic kilometers of estimated depletion. Reservoirs, 7 cubic kilometer decline. And then soil moisture storage pretty flat because you're irrigating, and then groundwater storage about estimated 30 cubic kilometers. And then comparing, so this is the groundwater storage data, and then comparing that to estimates from the groundwater level monitoring from data from DWR. You can see pretty good correspondence between the two, but I'm not sure that that's not just cancellation of errors and wishful thinking. But I mean, we've got some fundamental things to think about with that. I mean, GRACE should not respond to depletion in the confined zones because it's not a mass change, it's a pressure change, and we have to resolve some other issues related to that. So next I'd like to just talk a little bit about the High Plains region and the depletion there and how it compares with the Central Valley. So, I mean, you are fortunate in one way, you know in the winter if you're going to have drought problems in the summer because you're relying on the snowpack. When we have summer precip throughout the High Plains, we don't know whether we're going to have a drought the following summer. So we don't know how to accommodate it. So that's one advantage, if you can consider it that way. But so looking at the precipitation data, so this is the High Plains, the average precip is about 500 millimeters, but the contours are north-south. So it's wetter in the east and drier in the west. And here you've got this north-south gradient, you know, in precipitation. Also, the High Plains is generally elevated above other regions, and we have very little input from streams. I mean, the main ones are maybe the Platte River and the Republican, but there's not much. So we're relying almost totally on the precipitation that falls on the Plains region, and we don't have a lot of input from outside. And USGS has been doing a fantastic job of monitoring groundwater storage in the High Plains since the mid-80s. And this is Ginny McGuire's data showing no depletion in Nebraska and then large depletion in Kansas and Texas. And so, you know, Nebraska does not like being lumped with the rest of the High Plains as being considered subjected to groundwater depletion. And so it's important to understand that. So why do you think that they don't have that much depletion in Nebraska? Anybody? Pardon? Population. There's nobody living in Nebraska. There are not many people living in the entire High Plains. They asked me to talk about the North China Plain, but I don't have time. There's like 2 million people, and there's 200 million people living in the North China Plain. So there's not many people living anywhere. Putting it back in and recharging. You know, I was at a meeting recently with electrical company people, and he said he had to irrigate his lawn because he had to recharge the groundwater. But you know, if he was irrigating with surface water, that might be true. You know, it just depends on the source. But if you're irrigating with groundwater, and here it's all groundwater, you know, there's 30% coming from the Platte River in Nebraska, so that is a factor. But it's not like they're irrigating less or using less. It's just that they have a lot of recharge in Nebraska. I mean, this is the sand plains, and this is recharge estimated from groundwater chloride data. You have a lot of recharge in the sand plains and no irrigation there. And then you've got surface water irrigation from the Platte. So both of those factors contribute to less depletion in Nebraska. And this is a soil map, so you can see very sandy soils up here. And here, these clay loam soils, you have no recharge. You have no recharge. Even when they flood irrigated, it didn't recharge. And we can see that from borehole data. And so it's a difference in recharge. Much of this was recharged in the Pleistocene time. And that's how the climate becomes important. So a few boreholes can give you a lot of information. You can model all you want, but if you don't collect some basic data. So looking at depletion in the high plains, then using, this is the ground level data showing depletion from 2002 to 2007. And this trend then from the monthly data is about 8 cubic kilometers per year depletion. And then the trend from the GRACE data gives a similar value. It's a one-way street in the Kansas and Texas. There is no, you can't do it sustainably unless you stop irrigating. There's no, because the recharge is very low, and they're depleting it 10 times more than the recharge in northern Texas. So it's more of a socioeconomic factor than physical. So how can we get towards more sustainable development then? So normally I think of these things as supply-demand things, and somebody said earlier they may be focusing a bit too much on the supply side. Reducing demand, more efficient irrigation. So in the high plains, a center pivot system is extremely efficient, and then they have subsurface drip now, which is less efficient because they have to add more water to get the water up to the roots. But they're salinizing the soil, they're building up salts. And they're not seeing the effect because they're irrigating cotton, and cotton is not very sensitive to salt. But in over 50 years, we've built up the same amount of salt as we've built up over 10,000 years in some of those soils. You could change irrigated to rain-fed ag, and they say long-term average, you get about half of the yield from rain-fed as you do from irrigated. We need some more information on the economics of that and trying to incentivize that. Increased supply, interbasin transfers, conjunctive use, which you guys are already doing, and increased storage. Reservoirs, traditionally we think of surface water reservoirs, but in Texas we haven't built new reservoirs since the 70s, and we've had a 45% reduction in per capita reservoir storage since that time. So groundwater banking. I mean, we can't do groundwater banking in the high plains. There's nothing to bank. There's no surface water, but you can here, and that's what I think is really nice. So this is Arvin Edison, been doing it since the 60s, and with these surface spreading basins and then recharging. But I guess, you know, these spreading basins may be recharging the shallow system, and it's important to consider where they're withdrawing the water, if it's the deeper system and how they might be connected, and what that is like. But these are data from Arvin Edison, and you can see, you know, they're building up storage over time, and then 76 to 77 drought, remove water from storage, and then build it up until 87 to 92, and then remove it and then build it up again. So it's really nice to see this sort of thing, and I think we'll hopefully be seeing more and more about that in the future. To summarize then, the connection between groundwater and surface water is different between arid and humid regions. In humid regions, groundwater discharges to streams, and also in some arid regions, but oftentimes in arid regions, streams are recharging groundwater. Irrigation is the elephant in the room, I think, in terms of groundwater depletion. Conjunctive use of surface water and groundwater can be very helpful if there is surface water available, and Central Valley you have it available because you transport it. And then managed aquifer recharge is also another possibility in these regions. But you can do that because you're transporting a lot of water from the humid region to the arid region, the same in Arizona. So we have a special issue of environmental research letters, Vladimir Smatkin and I, because we think this is a very important topic for buffering against climate extremes from droughts and floods. I mean, you can see from Australia, they had a 13-year drought, ended in floods. You need those floods to end the drought because you have such a long-term cumulative deficit. And so droughts are going to end in floods. And so if you can store that water, that's great. But I know in some of in Arvin Edison, that early water in 2010, when you had huge precipitation after the 2007-2009 drought, the water was so turbid that they couldn't store it. That it was difficult to store. But we need to try to manage these extremes, and I think groundwater banking is an approach to do that. Thanks very much.